It's obvious the unthinkable is happening. With all the recent media distractions, most folks never saw it coming. But a few did. Their guts told them something very wrong was going on. And now the headlines are proving them right. The people in charge keep telling you that everything's fine and to stop noticing. But you know better. Folks are investing in emergency food storage, and you should too. My Patriot Supply, the nation's largest emergency preparedness company, are the ones you can trust. Go to mypatriotsupply.com and secure their best-selling 3-month emergency food kits. Each contains tasty breakfasts, lunches, and dinners, averaging over 2,000 calories per day. Get at least one for each family member. My Patriot Supply also sells biomass stoves, off-grid room heaters for when the power goes out, gravity-powered water filters, heirloom seeds, and survival gear that may come in handy soon. Go to mypatriotsupply.com today. It's time to prepare for what's coming. mypatriotsupply.com.
This is Marshall Rabel with Hubbard Peanut Company. Give the gift of crunchy goodness this year with Hub's Peanuts. For over 70 years, our family-owned company has been cooking and packaging the finest Virginia peanuts in beautiful gift tins, perfect for your friends, employees, or clients. Choose from plain salted or chocolate-covered peanuts. Hub's Peanuts are the perfect way to say thank you, and with our ability to handle large orders, Hub's has you covered. Visit hubspeanuts.com to place your order. Hubbard Peanut Company, Virginia's finest.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on the Space Nuts podcast. Andrew Dunkley here, and as always, I'm joined by the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Formerly known as the Bad Professor. Yeah.
That was a cartoon show, wasn't it? I can't remember.
Probably it might be.
Yes.
Well, but isn't that what this is?
Sometimes it is. How you been?
Very well, thank you. All good. Still celebrating last week's great news about James's literary prize, my son James, which has sent us all into ecstasies. He got the whatever you call it, the award itself, the physical award. He sent me a photo of it because it came through the post, and it's a penguin walking out of a wall because it's the Penguin Literary Prize. I'm not sure what the wall has to do with it, but that's all right. It's good. It's very nice.
It could mean breaking through that publishing barrier. You know, that is such a big, thick, heavy wall, and most of us,
Yep.
you know,
Don't get it. That's right.
don't get past that.
No.
Yes.
Great stuff.
Now, before we get on to today's topics, we've got an email from Mark Snelson. Now, Mark has a mutual friend, Hannah, the airline pilot that writes to us occasionally, and sent us some amazing pictures of her travels around the world. And Mark's emailed us with something similar. He says, you probably remember my name. Fred has answered a couple of my questions in the last few years. My colleague Hannah gave me your email address. I am also an airline pilot, and I thought you and the professor would like to see these pics. I don't imagine they are suitable for the podcast. Well, we're going to talk about them, but I reckon you guys will enjoy them anyway. This was on a flight from Midwest USA to the UK a few days ago. As today is the solstice, which is a couple of days ago our time now. The pics not only show noctilucent clouds, but illustrate quite nicely how it doesn't get completely dark, even at the not so northern latitudes of our Atlantic crossing that night. 53 degrees north was the furthest north we got. We would often be much further north out of the Midwest via a great circle, but the jet stream dictated that this was the most efficient routing. What was remarkable about the noctilucents was the sheer extent of them. I was taking pictures from Newfoundland for about 2 hours, most of the way to Ireland before the sun rose. There was a band line of them visible for over 1,000 nautical miles, probably longer if the sun hadn't ruined it all. Anyway, I hope you like them. Keep up the good work. Best podcast there is. He obviously only listens to this one. Best wishes, Mark. Mark, thanks for the photos. They are incredible. You can even see the curve of the Earth in these photos. Quite remarkable images. And as he gets closer and closer to these clouds, they become much more vivid and quite impressive. And I wonder if we can use one to demonstrate what he's talking about on our podcast banner photo when we set it up this week. I'll ask Hugh if we can do that, but they look amazing. Now, Fred, you might want to remind people what a noctilucent cloud is.
Yes, I will. Can I make a comment, though?
Yes. And
I'm really sorry to be pedantic here, but the curvature is the image distortion in the camera. You don't see the curvature of the Earth from the height of an aircraft. You've got to be much, much higher before you start noticing it.
It was a nice thought, though.
It's a lovely thought, yes. And I'm sorry to be the killjoy in this, but the horizon's flat.
I'm used to it.
The horizon's flat from an aircraft. I just checked latitude 53. That's quite right. That's it's not really very far north at all. In fact, Edinburgh, where I used to live, is in Scotland, is 56. So you're kind of the latitude of the Midlands in England, and it is true. In when I was a young astronomer doing my uni stuff in Scotland, it didn't get fully dark between the end of May and the beginning of August. It was always twilight through the night because of that northerly latitude. And of course, if we'd been at the height of an aircraft, 10 kilometres or so, we would have seen that beautiful band of orange along the northern horizon, which we have got the image of, which I hope we'll be able to show people. So noctilucent clouds are very high altitude. If I remember rightly, 90 or so kilometres. I should look it up, but it's that
I did
kind
look
of
it up the other day. It's between 80 and 100 kilometres. So,
okay. Oh well, that's not bad. And they're ice crystals basically, but they're forming in a very rarefied part of the Earth's atmosphere, and they're illuminated by sunlight because of their height. They're illuminated by sunlight that is not visible at all from the ground. It's completely dark from the ground in what we call astronomical twilight, which is when the sky is totally dark and sees no scattered light from the sun. So, and they've got this ethereal whitish colour to them, different from something I think you and I spoke about it's a couple of years ago now, but the last time I was up in far northern Scandinavia on our aurora hunting, we had these marvellous displays of what are called polar stratospheric clouds. They're iridescent. You see them during the day, and they've got the most stunning colours in them. They too are very high. I don't think they're as high as noctilucent clouds, though, and they have a different effect to them. And as I said, you see them during the day. Noctilucent, as the name suggests, night glow or night light. Yeah.
Yeah, because they're not visible when the sun rises, are they? You can only see them with the sun hitting them from beyond the horizon.
Yes, yeah, that's right.
Yeah, they're very nice, though, Mark.
Yeah, stunning images.
Beautiful images, yeah. I hope you don't mind if we use one. I think it, and maybe I could put them on the Space Nuts podcast group Facebook page too. So
there you go.
Email me, Mark, and let me know if that's okay. You might not want me to share those, but just give us a yell. Although by the time you hear that, the podcast will be out and I'll have already used one. It's a rocky slope, isn't it? Copyright. Now, today, Fred, we will be talking about Venus because they may well have discovered that it is geologically active, which comes as a bit of a surprise. We're also going to talk about... Now, I read this article and it just... and I've read it twice and I still am trying to get my head around this, but my pre-seed attempt at explaining this... a new discovery about the colossal galaxy cluster rotation is what I'm calling it, but that's just my rudimentary understanding of what I read. I might have glanced the target there. Rusty's sent us a question about the moon's position at certain times, particularly around the solstice, which we've just had. And Ben wants to talk about jets, not the ones with wings, the ones out in space that spit gunk everywhere, I think. We'll talk about those as well. But let's first go to Venus, Fred, a planet that we all thought was long dead with its runaway greenhouse effect. And now we're starting to see a very different picture, and it looks like it may well be active in some respects.
Yes, that's right. And, this is a very timely piece of research that's just been published by scientists at the North Carolina State University in the USA. Because of the fact that we've just had the announcement that NASA is going to send 2 probes to Venus later in the decade. And it's been a big question for a long time. Is Venus tectonically active? Does it have tectonic plates like the Earth does? And there's been, people have hedged their bets either way, I think. Some people say no, some people say yes. And people do provide little snippets of evidence either way, which seem a little bit contradictory. But now we've got, from this research done at North Carolina State, we see some really good evidence, I think, that, and it's certainly the most convincing thing I've seen, that says that while Venus is still, to all intents and purposes, is a dead world because the surface temperature is 460, I think it is, degrees Celsius. It's impossible for any kind of living organisms we know about to live on the surface. Maybe something in the atmosphere. Despite all that, there is some sort of geological activity, but it's different from the plate tectonics that we have here on Earth, which I guess most people are familiar with. Really large chunks of the Earth's crust are kind of solid, but the crust itself is broken up into these very large chunks which slip and slide and cause eruptions and volcanoes and earthquakes. There's a lovely piece. I'll just do a plug here. There's a lovely piece on the ABC website, Australian Broadcasting Corporation. They've done a piece on the Alpine Fault in New Zealand, which is overdue for a Richter 8 earthquake, and it's something
right.
you can find on the web. Yeah, it's they happen every 300 years, and we're overdue. And that's that is a absolutely physical and visceral evidence of plate tectonics happening on the Earth. What seems to be happening on Venus, and I should explain that this comes from radar imagery. There was a spacecraft whose name was Magellan, a NASA spacecraft that orbited Venus in the very early 1990s, equipped with radar, and did radar surveys of the surface because, of course, you can't do any visible imaging because the clouds are so thick and opaque. So Magellan mapped the surface. But what is happening now is people are revisiting those radar images because we've now got the most sophisticated algorithms for dragging hidden features out of data like that. And I think that's what's happened now. These scientists have used the NASA imagery, but it is enhanced, and what it shows is a surface that clearly has fragmentation marks in it. You see these, and again, it's worth checking this out on the web. There are images to be seen where you can see linear features, straight lines looking like fault lines, but they're following a regular pattern, looking almost like a pavement, a paved area of a street, for example. They're relatively square, these blocks, and it's broken up into these patterns, which are much smaller than the Earth's tectonic plates. But the evidence seems to be, because of these marks, that they do behave like tectonic plates. Banging into each other and dragging alongside each other and things of that sort. That one of the suggestions that's been made is that it's like pack ice on a frozen lake, which is a very nice analogue. And one of the authors, Paul Byrne, who's at North Carolina State, he's quoted as saying, "We've identified a previously unrecognized pattern of tectonic deformation on Venus, one that is driven by interior motion, just like on Earth." And he says, he goes on to say, although different from the tectonics we currently see on Earth, it is still evidence of interior motion being expressed at the planet's surface. And by that interior motion, what they mean is the convection currents that rise through the mantle. That's how plate tectonics is driven on Earth. We've got these convection movements in the sort of softish rock that surrounds the core of the Earth, but is underneath the crust. So that's what drives plate tectonics on Earth, and presumably something similar is driving these much smaller plates on Venus.
Yeah. So, I mean, aside from the fact that it's got a runaway greenhouse effect, it's similar in size to Earth, and it's more like us than Mars in that respect. And I suppose if you were able to stand on the surface, the gravity would be not much different to here.
Yes, that's correct. Yeah.
So everything about it is similar to Earth, except for what's happening in the atmosphere. But we're catching up. We're not far. We're not that far behind. We're working on
best.
it.
Yeah.
We're working on it.
Yeah.
But now I'm wondering what's happening on the inside and how similar that is to what we are experiencing on Earth.
So that will be the next step, to try and explain why there's this difference in the tectonic activity. Something we have known, and in fact wrote about it in the new kids book, that Venus's surface is volcanically active, perhaps until recent times, and in fact even now. We don't know that, whether there are active volcanoes on Venus. People seem to think that they probably are. Yeah. But there seem to be major lava flows, which is echoed in what this scientist Paul Byrne says. He says, we know that much of Venus has been volcanically resurfaced over time. So some parts of the planet might be really young, geologically speaking. But several of the jostling blocks have formed in and deformed these young lava plains, which means the lithosphere, that's the crust, fragmented after those plains were laid down. This gives us reason to think that some of these blocks may have moved geologically very recently, perhaps even up to today. So This sort of pack ice pattern is a very exciting thing.
So Venus is most likely having quakes, just like Earth does.
Yeah, that's
and
right.
fairly frequently by the sound of it.
Indeed, that's right.
Yeah, quite an incredible discovery, and clearly more to learn. And with new missions headed that way, it could be some pretty exciting discoveries. Unlike Mars, we won't be able to one day set foot on Mars, not with the current technology, and Venus, and wander around. Putting a rover down wouldn't work. We've put probes down there; they haven't lasted very long.
That's right.
And there was that famous case of the lens cap, so which melted to the lens, and they couldn't take any pictures. But one day we might figure that one out. But it's a pretty exciting discovery. So more to come from Venus, from the surface and its interior, by the sound of it. This is the Space Nuts podcast. You're with Andrew Dunkley and Professor Fred Watson.
Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024. And no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
0G, and I feel fine.
Space Nuts.
And a big hello to our patrons, the people who put a few dollars into the jar every week that we keep on our counter at the Space Nuts headquarters. Got a few quarters in there now, and we really appreciate the financial support we get. If you would like to become a patron, it's as easy as going to our website and clicking on the Support Space Nuts button, where you can choose whatever way you want to support us financially if you so desire. It's not mandatory, but it does help to kick the can. And it can start as low as $4.50 a month. That's Australian, so even cheaper for everyone else in the world, basically, because of the value of our dollar at the moment. But you can do it that way, or that's through Patreon, or you can do it through Supercast, or you can do it through the shop, or you can do it through PayPal. whatever way you like. And thank you to those many, many people who are patrons of the Space Nuts podcast that continue to support us. And we're still working on ways of giving back. So we'll let you know when we've figured all that out, which, could be, less than a decade or so. We're very, very helpful that way. Now, Fred, let's move on to this. It's another major announcement / discovery. They've been mapping the motions of galaxies. Now, we're talking a massive scale here. This isn't just sort of looking at us and Andromeda and those other tiny little unfortunate galaxies that we're eating at the moment. We are talking massive super galaxy clusters and how they're all linked and how they're all rotating. They have now basically confirmed that there's this big movement going on a colossal scale, and I love that word. And now, and this is so typical of astronomy. They've made the discovery, they've announced it, but they don't know why.
Yeah, that's right.
Am I right? I mean, is that what we're talking about? Because I read the story, and it really just sort of spun my brain out of control.
So I keep telling you, Andrew, you don't need me at all.
Yes, I do.
So to step back from the news, just to remind people of what the big picture is. When we look deep into the universe, we see galaxies, of course, as you mentioned. We also see clusters of galaxies. There's a very big one nearby, the Coma cluster. And these are sometimes thousands of galaxies. But when you really start looking at the big picture, and you're probing now to usually quite significant distances in the universe before you can see this picture emerging. I'm happy to say I've been on the periphery of being involved with this kind of work. Actually, not that much on the periphery because I built the instrument that did some of it.
Cool.
Back in the 1990s and 2000s, and it comes. Our knowledge of this phenomenon comes from what we call galaxy surveys, where you basically map in three-dimensional space where galaxies are over as big an area of the sky as you can. And in fact, we did it for the whole of the southern sky with something called the 60F Galaxy Survey, which I was project manager for back in the early 2000s. So, but there are other surveys that have been done with similar technology. We do it all with fiber optics, and I have time to talk about that. But that was what I helped to sort of pioneer back in the early 1980s. There was a group of us throughout the world who tinkered around with these fiber optics, knowing that the end product could be measurements of galaxies thousands at a time, and now they're hundreds of thousands at a time and millions at a time, with similar kind of technology. So when you do that, when you look at these maps of galaxies, you find this structure within it, which we call the cosmic web. And it is reminiscent of, walking into a room that's not been cleaned for decades and finding the whole place.
You're not looking behind me, are you? I mean,
well, that's that. That's where I got the inspiration from, Andrew. There's this web. It's almost, it's also like a kind of honeycomb. It's not perfectly hexagonal, but it's strings of galaxies stretched over colossal distances with great voids in between them where there aren't any galaxies. And that's called the cosmic web. The voids, the honeycomb cells, if you want to use that analogy, are typically, they're hundreds of millions of light years across. They're enormous. This is a structure on the grandest scale, and we think it's actually the result of the way matter behaved in the immediate aftermath of the Big Bang. You can see the seeds of it in the cosmic microwave background radiation, where we're looking back to a time before the first galaxies formed. But there is structure in the temperature of the cosmic microwave background radiation, which suggests that what you're going to get when you get matter, forming stars and planets and galaxies, you're going to get this web-like structure. So the structure is well established. But what has happened now is that people have looked in detail at what we call the filaments, the sort of cobwebby stuff that joins, that's the scaffolding, let me put it that way, of the cosmic web.
Yep.
And basically, these filaments link together gigantic clusters of galaxies, which are at the what you might call the nodes, the places where things cross, the corners of the hexagon, if you think of it as a honeycomb. So looking in detail at that, and this is scientists from AIP, an institution I know very well because I've worked closely with them, the Leibniz Institute for Astrophysics in Potsdam. They've worked with scientists in China and Estonia. And what they've discovered is that these filaments, long tendrils of galaxies, they actually spin.
Yeah.
And that is a brand new discovery. And it's a record breaker in the sense that we've never seen rotation on such a vast scale before. We see rotation in pretty well everything in the universe, but a rotation of the filaments of galaxies. And remember, these are made of, galaxies which are themselves significantly separated, that they're actually rotating. So that's a new discovery and quite a surprising one. Although I have to say, I was interested to see that theoretical astronomers, these are the people who work out the models of what the universe looks like, they've suggested that these things should spin. And sent people off looking for them, which is why the scientists at the Leibniz Institute have discovered them, the spin of the filaments in the cosmic web. How did they measure it? Well, by the same way that we always measure rotations, which is using the Doppler effect. The fact that light coming towards you is shifted towards the blue, light from an object moving towards you is shifted towards the blue in the spectrum, light coming from an object moving away from you is shifted towards the red, hence the term redshift, although that is nuanced slightly differently, but on the scale of the universe. But it's the Doppler effect. That's what's allowed the scientists to work out the galaxies on one side are coming towards us, in effect, despite the fact that they're all moving away because of the expansion of the universe, but they're more coming towards us than the ones on the other side, which are more going away from us. So that's how the rotation has been detected. And exactly as you've said, even though this is predicted, it's a struggle to understand why the rotation should be there. It's another aspect of it, just one final thing, Andrew, before I let you get a word in edgeways, it's the galaxies themselves actually move along these filaments. The filaments are made of galaxies. So what you've got is this, imagine an individual galaxy. It's moving like a corkscrew. So it's moving along the galaxy, and it'll wind up in a big cluster of galaxies at the corner between your tendril and the next one. But they're moving along in this spiral orbits, basically, along as well as rotating. So the whole thing is, this whole filament is rotating as the galaxies move along it. And it's up to you to work out why that is happening, Andrew.
Yeah, I've got my pen here. And
yeah, good. Actually, I should mention pens because a pen is or a pencil is a good analog for the overall shape of these things. They're that long and that thick, but scaled up to millions of light years.
And are they sort of spinning on an axis while everything inside's rotating, or we've got multiple movements happening at once?
There may well be, but that would be a much smaller. It's spinning, around the line of the pencil.
Okay.
If you imagine a pencil being twisted, that's what's happening.
Right. Wow. And of course, that opens up the big question as to why and
Indeed.
How it all started, and it could go back to as far as we know back. You don't know. Yeah.
You could. There's another line you could take with this. So the reason why planets revolve around their parent stars is because planets and stars are formed from clouds of gas and dust. And those clouds are ginormous. They're much bigger than the solar systems that they form, because they often form many, many solar systems within them. But they've gas and dust is a fluid, and so they've probably got little eddies within them. And it's those eddies that lead to the rotation of planetary systems and stars, because as a if you've got something that's collapsing under its own gravity and it's got a little tiny set of eddies in it, there'll always be one eddy that's more strong than another one. So that becomes the preferred direction of rotation. And as it collapses, that rotation is locked in ever more solidly by something called the conservation of angular momentum. And so things rotate faster. And that's how you've got, a flat planetary, protoplanetary disk in young solar systems and the planets forming in a plane. Now, the thinking regarding the cosmic web is that there is no overall rotation of the universe, but there might be sort of eddies of rotation within the material of the early universe that could have given rise to a similar process, a rotation of these tendrils. I'm not making that very clear, but it's probably the rotation is probably a fossil of just a general eddy rotation within that bit of the primordial fireball when the universe was created.
That's what I was trying to say. So, thank you. I wouldn't have said it that well, but that's what I was trying to say. Yeah, it's just a sort of a spin-off of the original effect.
I mean, you're as capable of making things up as you go along as I am, which is...
That's how I write books.
yeah.
Oh, dear. No, it's fascinating. And again, trying to get your head around the scale of this is just... Yeah, it's so hard to imagine the massive scales we're talking about. Millions of light years.
Yeah, hundreds of millions.
Structures of galaxies and these filaments and the way they're moving around. Do we know how fast this rotation is, or they haven't figured that out?
I looked for that. I think it's in the original paper, which I didn't have a chance to look back at. But it's clearly not once a day or anything like that.
Yeah.
It's probably spinning on the scale of many tens of, if not hundreds of millions of years for one rotation.
Wow, extraordinary. Well, hopefully one day they'll get more answers to this one. It might answer other questions if they figure it out. It's
that's right.
Quite amazing.
And of course, it's all intimately linked, Andrew, with dark matter, because we think that dark matter is the reason why this cosmic web forms the way it does. Because dark matter is one of the principal agents of gravitation. That's right, superglue.
Yeah. Okay. We may well hear more about this in the not too distant future, a couple of billion years when it's done its first lap. Yes. And by the way, I met my son's friend Eddie yesterday, and he is very strong, as you suggested.
Good.
This is the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
And thanks for joining us. And thanks to our YouTube followers who are increasing in number. We've got 1,740 subscribers to our YouTube channel. So if you would like to watch the Space Nuts podcast, God knows why you'd want to, you can do that at youtube.com/c/spacenuts, or just do a search in YouTube for Space Nuts Podcast and you should find us. And to make it easier on the listening and viewing process, we've broken it up into segments. Now, I know there's been a few remarks about that on our Facebook page. Most people like it that way because they can absorb more of the podcast in, chewable chunks rather than one big block, which seems to be the audio preference. But with the video preference, we've broken it down just so it's easier for you to deal with. So instead of those block segments, we're down to, segments of 12 to 15 minutes-ish. Depends how much talking we do, I suppose. But, I think you might find that a little bit more appetizing, perhaps. We'll see how it transpires. But we're just sort of doing that as a bit of an experiment. A couple of people don't like it, and that's fine. But the majority seem to prefer to have the YouTube videos in smaller clusters, unlike galaxies we were just talking about. Now, Fred, let us move along to our Q&A portion of Space Nuts today, and our old friend Rusty is back in action.
G'day, Andrew and Fred, the lovable larrikin and nature's true gentleman. It's Rusty from Donnybrook. Did you miss me? I have a quick question. Why does the full moon travel almost directly overhead, both in southern and northern hemisphere, around winter solstice? Cheers, guys. Loving your show.
Thank you very much, Rusty. I'm having a bit of trouble here, but when we get these audio questions, the system automatically translates it into text. Well, the lovable larrikin was translated into. I'm trying to get to it, but it keeps blocking my attempts. Here it is. Lovable arrogant. I am apparently, according to the translation. I'm a lovable arrogant. That's pretty accurate, actually.
I'm not going to go. I'm not going to touch that one.
That's all right. I've already done it. Nice to hear from you again, Rusty. And the position of the moon during the solstice, almost directly overhead. Why is it so?
It's a good question, and one that I always used to find strangely cheering, which I'll explain in a minute. It's not almost directly overhead. It's what it's doing at the winter solstice. The moon's path through the sky, when it's a full moon, if you've got a full moon right on winter solstice, this is the perfect storm, although around about the same time, it's, within a month either side of the solstice, this works well. The moon's path through the sky at the winter solstice is pretty well exactly the same, within a few degrees, the same as the sun's path through the sky during the summer solstice. And that's because if you think about it, what you've got at full moon is you've got the sun, the earth, and the moon in a straight line. The sun is at its lowest in the sky, and so that means the moon is at its highest in the sky when it goes around. And so it's noticeably so, though it's not quite directly overhead. Actually, it's not that far off because in our latitudes here in Australia, we're not very far. I mean, there are tropics within Australia. The Tropic of Capricorn runs through Queensland, so that is why you would see the full moon directly overhead up there in the north of Australia at the winter solstice. The reason why it used to cheer me, Andrew, was because I used to get a bit fed up in the British winter, both where I grew up in the north of England and where I was educated later in Scotland, because the sun in winter kind of skirts the horizon it was 13 degrees at its highest where I grew up in Yorkshire, and it's less in Scotland. It's lower. It's about 9 degrees. So seeing the sun that low in the sky, I always found a little bit depressing because it wasn't there for very long. It rose and then set again. But the moon, when it was full, did exactly what the sun does in the summertime. And you could see it all night and shining brightly from high in the sky. And it just provided me with this slight reassurance that, yes, summer's going to come again.
Which wasn't very often because of the fog and the rain. But,
that's right.
And the cloud.
Yeah. So. It's really interesting. Now my life is turned the other way, though, having lived for 40 years in Australia. One of my favourite things to do when you can travel is to go up to far northern Scandinavia in winter when the sun doesn't rise at all. Yeah. And it just gives an entirely different attitude to winter nights and winter days. The days are not dark because the sun's not that far below the horizon, but there's no sunlight, so you get this lovely long twilight and often get some beautiful.
I'd love to experience that. I know it sounds corny, but it would be my great thrill to get up to Sweden or somewhere like that in the it's the opposite time of the year in summer, and play golf at 1 o'clock in the morning. Because
you could do that. Yeah.
It's still light, and they do that. They do that.
Yeah, they would.
I suppose being in Australia as we are, we don't know how lucky we really have it, because we do, even in winter, get long periods of sunshiny days. And even now, even though we're approaching July, we've had some extraordinarily mild days this last week or so, aside from the rain that I experienced in Sydney the other day. But we're getting a top temperature of 19 one day next week, which in winter is unthinkable.
On the other hand, when I was there the week before last, we got snowed in at Siding Spring.
Yes.
So it's,
Yes, we used that image on the podcast title page.
Okay.
But it can be. I do like living here for that reason. We get these extraordinary winters where it's not. We whinge about it.
Yeah.
It's not nearly as bad as many other parts of the world where millions and millions of people get suffer through the cold and the snow and the slush and the ice. And you can have that on your own. I can play golf all year round where I am. Yes, it is. Did we finish answering Rusty's question?
We did. Thank you. Thanks, Rusty. It's a great question, and as you can see, it touched a little tender nerve on my part.
Yeah, I couldn't imagine living days and days and days for weeks on end without the sun rising. No. But I'd love to see it just for the experience. Okay, thanks, Rusty. Lovely to hear from you. Hope all is well in WA. Oh, by the way, you mentioned how the sun reaches that direct point over the Tropic of Capricorn. There is just south of Rockhampton in Queensland, I wouldn't call it a monument, but a monolith of some kind, which is designed for that very experience. You can stand under it at an exact time during the summer solstice and look straight up, and the sun will be directly inside the funnel of this thing they've built. I've seen that thing, but I wasn't there at the right time. But I can't think what it's called. But it's right on the Tropic of Capricorn, that monolith, and it's designed to give you the experience of where the sun will be at the exact, I think it's 12 noon. Or something to that effect.
It is.
It's quite extraordinary. So if you're ever up there, have a look for it. I think it's near the Bruce Highway, up there somewhere. Righto, let's move on. This is a question from Ben.
Hey, Space Nuts. This is Ben from Massachusetts. I have a question about relativistic jets. So I believe this is emitted out of the center of galaxies, the quasar or supermassive black hole. There's some kind of energetic jet that's released, and it has the question here is it has some kind of shape to it. It seems to vary in like direction, magnitude, and thickness. So I was wondering if you'd tell me about these jets. What do they mean? What can we learn from their shapes? Thanks. Bye.
Okay, do you know what he's talking about?
Well, yeah, I do. Yeah, and it's a great question, and one that touches on stuff that is completely counterintuitive as to how these jets form. So Ben is right. They are emitted from the centres of what we call active galaxies, which in their extreme form are called quasars, which are very active galaxies. And they're caused by the supermassive black hole in the centre of the galaxy going through a highly active phase of gobbling up their surroundings, basically. The accretion disk, this disk of material that forms around a galaxy, around a supermassive around any black hole, actually. If it's got material around it, it will be drawn into an accretion disk. But the supermassive ones have supermassive accretion disks. So stuff is swirling around in this disk. It's highly energized by the friction, the fact that there's these things, particles, bits of star are colliding with each other and things of that sort. And so that's why the accretion disks are emitting radiation and X-rays as well. Excuse me, I'm going to cough, Andrew. An accretion disk in my throat there. Sorry about that. The swirling material, some of it gets sucked into the black hole as you'd expect. But this is the bit that really goes against all logical thinking. Some of it gets squirted out at right angles to the accretion disk. In other words, along the north and south poles, if I can put it that way, of the black hole. If you think of the accretion disk as being the equator, the north and south poles are where these jets of material squirt from. And as Ben said, they are relativistic. That means their speeds are not very far short of the speed of light.
Yeah.
And it's not just material, it's radiation as well. Now, how on earth can that happen? How can you have a swirling disk of material, some of which suddenly finds itself being propelled at right angles to the disk?
You play golf. That's how you do that.
There you go. Well, this might be useful to you then, this little hint that I'm about to drop. We think it's all done by magnetic field. So if you make sure the Earth's magnetic field is in the right direction next time you get your 5-iron out or whatever, everything will be all right. It'll go at right angles to the direction you think it's going to go in, which is what happens in the accretion disk. So yeah, intense magnetic fields, essentially, they funnel this material into really quite narrow jets. As Ben said, it's interesting, what's their thickness? They're actually really quite narrow. In fact, there's a technical term for that. We say it's highly collimated. Collimated means when things are moving in a parallel direction. And so a collimated jet is one that is almost focused on infinity, if I can put it that way. The jets, the material is moving parallel. Now, often when you see pictures of radio galaxies, you see these jets, and they're not perfectly smooth like that, the way I've described. They've got knots in them, knobs in them, and bits of lumps, and on very large scales they billow out into these clouds of material at the ends of them. And so what's happening here is, first of all, some of the blobs that appear on these relativistic jets are formed because the accretion process is not regular. There are times when there's more material being sucked in because the star cluster's been pulled in or something.
Yeah.
And that produces a blob in the relativistic jets. You get a blob of debris that's moving away from the black hole. But the sort of billowing out effects are caused when the relativistic jet interacts with the medium around it. And it might be what you might call the interstellar medium, which is the space between stars in a galaxy, or the intergalactic medium. That's the space between galaxies in a cluster of galaxies. So it's all very rarefied. The interstellar medium is rarefied. The intergalactic medium is even more rarefied. But there's still enough of it that when you get this stuff clouting into it, you get a billowing out effect of a strange-looking cloud being formed. And they emit radio waves. And that's why often when you look at radio galaxies, you see these billowing clouds of material that are at the ends of the relativistic jets. I hope that answers the question.
I hope so too. Yeah. You talk about things being counter to what a black hole does, and these things coming out when a black hole's power sucks everything in. How do they not get sucked back in?
But actually, the answer to that is because they are beyond the event horizon. These jets form sort of outside the event horizon, where everything is getting sucked back in, including light. A lot of, the material is, I find it very hard to get my head around it, but the theory works that you've got these intense magnetic fields. So they are sort of comparable with the gravitational force of the black hole itself. Magnetic fields of enormous intensity, which focus these jets and away they go. So you can escape a black hole, but of course it hasn't gone into the black hole, this material. It's swirling around the outside of the event horizon. Okay.
All right, there you go, Ben. Hopefully
good question though, Andrew.
Solved, yes, indeed. Solved your little puzzle. Yeah. Fred has all the answers. He knows everything. He's just holding back.
I wish.
Yeah. Appreciate it. And don't forget, if you've got a question for us, you can go to our website, spacenutspodcast.com, click on the AMA tab, and there you'll find a way to send us a question, whether you want to send us an audio question by pressing on the record button and just stating your case with your name and location, or you can use the email interface and send it to us in a text form. We take them both, and we're going to be testing some new possibilities in the future with a platform we're looking at that may well enable us to get our audio questions a different way. But yes, that's still in a trial phase. But the way we're doing it now works particularly well. So if you'd like to send us an audio question or a text question, spacenutspodcast.com and click on the AMA tab. And while you're there, click on the shop button as well and check out the vast array of product that I'm looking at now. We've got hats, we've got mugs, we've got stickers, we've got spiral notebooks. I didn't mention them the other day. We've got beanies, we've got socks, we've got flip-flops, we've got bomber jackets. There's just so much to choose from at the Space Nuts shop, which you can find at spacenutspodcast.com. Fred, that brings us to the end of episode 258. Thank you, sir. Greatly appreciated.
It's a pleasure. Good to talk. It's some interesting stuff, and there will be more interesting stuff next week.
Indeed there will. Looking forward to it. Thanks, Fred. Yep. Take care. We'll talk to you
later.
In a week or so. Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast, and to Hugh back in the studio, a big hello and thanks for all that you do. I know he works very hard behind the scenes, filing his nails and, giving himself a facial scrub and things like that. But he does other stuff as well, but he never tells me about it. But thank you, Hugh, and thank you for listening and or watching the Space Nuts podcast. We'll look forward to your company next time. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.